5 units. And so we're saying that is the tension in the string. That was the first harmonic. This time I put it someplace else. Grab that for now. So the first harmonic, that's the simplest pattern. How many waves is that?
Half.
Yes. That's half of a wavelength. So the wavelength would be 2L. So let's figure out what that distance is. This was, I'm hoping, lined up so that I can just do this. Am I at the right, am I in the right spot over there?
Yeah.
This requires more coordination than apparently I have. So what about there?
Close enough.
All right, so it looks like it's about 107.5. So L, 1.075 meters. So what would the wavelength be? Oh, use that one. So I have the wavelength, I have my linear density, I have tension. Well, first I can find how fast the wave must have been traveling based upon this formula. Then I can figure out what frequency we are predicting with that. And we can then compare it to what the actual frequency is. So let's do it. So the speed of the wave would be the square root of the tension, 12.25 newtons, divided by the linear density, which is 0.00141 kilograms per meter. Nope, that's not the right number. It does not want to erase. 0.00104. Now it wants to erase. Zero. Zero point 0.00104 kilograms per meter. So what do we get as the speed of the wave?
Meters per second.
108.52.
Yes.
That should be equal to the frequency times the wavelength. Well, that's my wavelength right there. So frequency times the wavelength is equal to the speed. So frequency times 2.15 is equal to 108.52. And what do we get as our frequency?
50.47 hertz.
50.47.
Yes.
And the prediction was 60, and that thing's vibrating at 60 hertz. And so we're off by, there's about 17% error. Not great, but it is what it is. Now we can adjust this scheme slightly. So ordinarily it does 60 hertz if I plug it straight into the wall. Instead, what we're going to do is play with the frequency. All right, right now it's vibrating at 100 hertz. If I want to get I got 500 grams on here. If I want to get the first harmonic, am I increasing the frequency or decreasing the frequency?
Decrease?
Is it decrease? Any particular reason?
I feel like if you decrease how often the wave occurs, it lengthens its wavelength.
Okay. That's the second harmonic. I think that does it. 38.3 hertz. Well, you were right. Let's see. That's an on-off switch. All right, so I have frequency times the wavelength is equal to the square root of the tension over the linear density. So the wavelength would be equal to 1 over the frequency times tension over lambda. I know that the wavelength, so we're going for, that was first harmonic. The wavelength is 2L, so that's going to be equal to 2 times the length. Actually, I want to solve for frequency. So the frequency would be 1 over 2L times the square root of tension over linear density. So we can make a prediction of what the frequency would need to be. The tension, we've got a 500 gram mass there, and so we would predict the frequency would be 1 over 2 times 1.075 meters times the square root of 4.9 newtons over 0.00104. That's from here. What do we get? $36.89
Yes.
units.
Hertz.
And we had 38.3 hertz. Not too bad. Questions to hear? All right, sort of shifting gears just a little bit, still dealing with oscillations. Say I have a spring here. I have a spring that hangs down a certain amount. I add 50 grams to it, to the end. It obviously stretches more. Let's think about the forces acting on the mass here. What are the forces acting on the mass?
Acceleration due to gravity.
I heard weight and what,
Same thing. Weight.
and
Tension.
in this case, since we're dealing specifically with what we'll call a spring, and some sort of elastic force. It would be a tension of sorts, but we can be more specific. So weight, so it hangs down a certain amount, I add mass to it, it will hang down more. So I have weight and I have tension. Some spring force. That spring force is related to the spring constant times the distance that stretches. So let's set that up. And,
Austin,
yeah,
can you explain when we use k times delta x and when we use 1/2 k delta x squared?
the 1/2 k delta x squared is the potential energy. This is the force. All right, we're going to base this on Hope. Stay. So when I add mass to it, the question is how far does it go down? That's right. So right now, the bottom is 37.9 centimeters from the base. Just 37.9. I add a 50 gram mass to it. Now when it hangs now, it is not level, so what I'm going to do is I'm going to, the distance to the sort of the downside and the distance to the top side, and just take the average of the two. I have had students go through 20 minutes trying to set up something so it hangs level. Sure, if you want to. So the low side is 18.7 centimeters, and the high side steady. That does not help. Still going with 18.7 there, and the high side 23.1. So it was, what were the two numbers?
You said 18.7 and 43.1.
23.1.
Not 20.
All right, so my average. All right, so how much did adding a 50 gram mass cause it to sink? What was the change in position?
17 centimeters.
All right, so therefore the spring, which is pulling up, and I have tension and the weight acting down, the weight, it's 50 grams, so 0.49 newtons. This was K times, you said 17 centimeters? Because it is in equilibrium, they're equal to each other, so 0.17 K is equal to 0.49. So therefore, K is 0.49 over 0.17, which is 2.9 something?
2.88.
2.88. See if I can actually write that more legibly. 2.88 units.
Joules.
Nope.
Oh, it's not, it's the spring constant, right?
Yep.
Newton seconds? Or
No.
Newton meters?
No. What were the units of the 0.49?
Newtons,
Units of the 0.17?
meters,
Therefore,
Newton meters.
no.
Newton per meter.
Yeah, that's a critical word there. So the spring constant is 0.28 newtons per meter. In other words, if I wanted it ideally, if it's an ideal spring, if I want to stretch it 1 meter, I apply 2.88 newtons to it. 2 meters, I would apply twice that. Suppose I doubled the number of coils, because this part up here is pretty much useless. If I just doubled, and so I have that much, if I doubled that, what would happen to the spring constant?
It'd be the same.
It would not.
Cut in half? Yeah, cut in half.
Yeah. So if I doubled the amount of coils, I cut my spring constant in half. Because,
So you would take less force to go a meter?
yeah. Because this, so with half that, I would stretch this half a meter. If I double the number of coils, I'd have a half meter from the other one also. So I'd get a full meter out of half the force. Now, something like this obeys what's known as Hooke's law. This is Hooke's law. Well, actually, Hooke's law, the spring force is equal to negative K delta X. Why negative? This is the force the spring exerts. What does negative usually mean when dealing with vectors?
Down.
Negative direction.
Pardon?
In the negative direction.
Okay. I'll spoil some of it for you. The opposite.
Basically what I meant.
I have two vectors here. The negative means that they're in opposite directions, which means this was displaced downwards. So my delta x is down, whether it's positive or negative. But the force the spring exerts is the other direction. The force always wants to turn it to equilibrium. If I took the mass off and it went back to its normal state like that, if I pushed up on it, my displacement is upwards, so the force is downward. So if I took this, attach my mass to it, and then I pull it down and let go, it's not in equilibrium, but it's going to oscillate back and forth. So imagine if we actually plotted the position of this with respect to time. So if I have a time axis going that way, what kind of curve am I tracing out with my finger?
Sinusoidal. Sinusoidal.
Say it again?
Sinusoidal.
Oh, yes. If we take it one step further, if I've got a nice ideal frictionless surface here, I've got a spring that's hanging onto it. Let's actually attach it from the other end and get a marker that might show up. So let's assume that's will be positioned at 0. I then add a mass to it and I stretch it out. So it starts out with some initial displacement. I'm assuming it's frictionless, so I'm not worried about that. I got weight acting down, normal force acting up. They will not affect any acceleration because the unbalanced force will be horizontal. This is some initial position. If I wanted to sort of, well, actually, let's do it that way then. I have weight acting down, normal force acting up. I have this spring force acting this way. What are my equations of motion?
Spring force equals mass and acceleration.
Okay? And?
Y minus W equals 0.
Now, the second equation we really don't care about. The first one is the one we care most about. So I have this, I know that's equal to negative K delta X is equal to M A. But recognize that acceleration is the change in velocity over the change in time. And displacement, try that one again, and velocity is the change in position over the change in time. So I have an equation here with a change in position and acceleration, and they are related to each other. So I need some function so that when I take the change of the change, I get pretty much what I started with, other than a negative sign there. And there does happen to be a set of functions that work for this. As Clay mentioned, sine waves or cosine waves. So let's do a little bit, for those who've had calculus.